Okay guys, to start off this lesson, I want you to take a look at the diagram and answer the question, what relationship does the line XY have to the line segment AB? So check it out. You've got some information marked. Notice there's the perpendicular marking. Those are right angle. And these tick marks showing that the two pieces of AB are equal in length or congruent. So we call that a perpendicular bisector. Now it's important to understand that AB is the victim here. In other words, XY is the line that cut through it and chopped it into two equal parts at a right angle. So so that means that XY is the perpendicular bisector of AB. XY is the important line here. It's the one that did the cutting. There's a theorem for perpendicular bisectors. Any point that lies on the perpendicular bisector of a segment is going to be equidistant to the endpoints of the segment. And so what we're saying here is if we pick any point, remember again, I'm going to highlight this, the perpendicular bisector here is XY. So if I were to take any point lying on that line, XY, then the theorem says that it's going to be the same distance out to A as it is out to B. For example, let's take a point right here. Right here, we'll just say that's X. If I go from X out to endpoint A or X out to endpoint B, those two distances are the same. So let's just make up a number. If this is 10 units out, then it's automatically going to be 10 units on the other side. They're just equidistant is what we call that. Another example, let's take point Y, a little bit closer to the segment AB, but still going out to the two endpoints from Y, I'm going to get the same measurement. Not the same as before with the 10s, but maybe this is 8. It's going to be 8 on the other side. So this is just some examples. Now, the converse of that. The converse is, it says that if you take a point, and, well, actually, let me start again. If you take a point and that point happens to be equidistant out to the two endpoints of a segment, so let me tick mark that, then that point lies on the perpendicular bisector of that segment. So we're kind of starting backwards here, and this is actually what lets our construction work. We actually build 2 points that are equidistant out from the endpoints, and that's automatically going to mean that there is a perpendicular line through there and that it bisects the original segment. So you're just going backwards. So let's just fill in the blank then. If a point is equidistant to the endpoints of a segment, then that point lies on the perpendicular bisector. So equidistant fills this in. Equidistant. Break it down. Equa is equal, and then distance. And that's what equidistant means. If I start at an equal distance out from the two endpoints, I'm going to be on the perpendicular bisector. Let's look at some examples to clarify. So the first thing you have to do when you are looking at perpendicular bisectors, you've got to make sure you know which line is the bisector. And so looking at this, it looks like my tick marks are here. That means that CD is the bisector line, and AB got chopped into pieces. So we want to pick points on CD that are going to automatically then be equidistant out to A and B. So let's fill in these blanks. We said CD is the perpendicular bisector, and that would be of AB. So let's find some answers here. We want to find the distance from B to C. So how far is it from B out to C? Well, C is on the perpendicular bisector. So going from C to B is going to be the same as going from C to A. C to A is 15, so C to B is also going to be 15. These guys match. B to C, C to B, whatever. This is 15. Okay, next one. Find the distance from A to D. D again. Here's D sitting on the perpendicular bisector. If I go out to A, I'm going to want to know this segment length. Well, I can find the answer by just going the other way over out to B. So here's the answer right here. It's 18 out to B, so it's also 18 out to A. So that's going to be 18. And last example, find A to E distance. A to E, well, E is on the perpendicular bisector. Just go straight up to A. You're going to find the same thing as if you went straight down to B. So straight down to B is 8. That means straight up to A is also 8. And it's easy as that. All right, so next one, we got to do some algebra I can see right off. But before I do anything, I'm going to answer the question, which line segment is the perpendicular bisector of which line segment? All right, as I look at this, I see, again, here's my tick marks. So AB is the bisected line. That means that CD is the bisector. So we fill in the blank that way. CD here in this picture is the bisector, perpendicular bisector of AB. Okay, so let's see how we can find the value of x. It looks like x is in a lot of these expressions, but I notice that here at point D, which is on my bisector line, if I go from point D out to A, I would expect that to be the same as from point D out to B. So these two expressions here should be equal, and that's how I'm going to set up my equation. I'm going to go with 2x is equal to the 3x minus 5. Those two distances are going to be the same. Let's subtract the 3x over, and I'm going to get a negative x on this side. These guys wipe out, and negative x equals negative 5, so that would mean that x would be 5. That's the value of x. Now let's use it in these next examples to find the distances. What's the distance from A to D? Well, of course, if x is 5, then 2 times 5 in there is going to give me 10. So from A to D is 10. Next one, find the distance from B to D. That's right here. Let's plug in that same value. X is still 5, so it's 3 times 5 minus 5. That's going to give me 3 times 5 is 15 minus 5. 15 minus 5 is 10. And so again, just notice those guys match. Distance from D out to A is the same as the distance from D out to B because D is on that perpendicular bisector. And finally, our BC segment. So BC we want to know, which is here. Well, that guy is going to match the same one on the other side, so x plus 3. Well, x is still 5, guys, so x plus 3 would be 5 plus 3, or 8. And that means I'm going to have 8 over here also, so that would be 8. Pretty cool. All right, now in our lab, we looked at perpendicular bisectors, and we found something kind of interesting, and I want to show you on an internet site. This is mathopenreference.com. But here's a picture of a triangle, just like the one we kind of did in our lab, and marked here is the center of that triangle. Now you might wonder why that's the center. In fact, let me just kind of drag things around. You're going to see when I drag this point A around that that center also moves. Well, how is that the center of the triangle? It's really weird. Did you ever think the center of the triangle would go outside the triangle? Well, it can. So what's going on here? Let me show you actually the details of what's happening. And this is what we did in our lab also. What they've done is they have constructed the perpendicular bisectors of the three sides of the triangle. So we notice that those three perpendicular bisectors all intersect, or what we call concurrent. They all three intersect in the same point, and that point is considered one of the centers of the triangle. There are many different kinds of centers, and we'll look at some with this unit, some other ones. But this is the center of the triangle in that it is equidistant out to the 3 points of this triangle. So it's the same distance from here out to A as it is out to B as it is out to C. Now let me show you how that works a little bit differently. When you look at this triangle, it's kind of similar to what we did in our lab. There's some perpendicular bisectors that are marked in here, and they want us to mark this information in the diagram. So let's go ahead and do that. It says that DG is the perpendicular bisector of TR. So when DG hits TR right here, it does it at a right angle, and it chops TR into those two equal parts. So I want you to mark it like that. FE is also a perpendicular bisector, but it's of TI. So when FE meets TI right here, again, there's a right angle that's formed, and TI gets chopped into two equal parts, or bisected. So there's that information, and if we were to do the third perpendicular bisector, we would also find that it meets where these others meet. So this point right here is what we call the circumcenter. And it's the center of the triangle in that it's the same distance out from that point out to R, out to T, and out to I. Now let me show you that with the compass. Here's my little computer compass guy, and I'm going to position him so that his anchor is right there at that circumcenter point. And then when I open him up so that he comes out to I, I'm going to get this adjusted a little bit. It's a little bit tricky. But notice that that distance to I, when I rotate it without changing the compass setting, it's the same distance to T. And around, clear around here, it also matches the distance from out to R. So on that triangle, those three triangle vertices are what we call equidistant from that point. Let me actually draw the circle that would go around it. And we draw the circle to show that that's an equal distance. Okay, so if you have a compass, you should try that on your own notes. And if not, grab one from me tomorrow and make sure you get that drawn in there. But the important thing to note is that if I were to go from that center point, that circumcenter point, if I go out to T, or if I go out to I, ooh, straight edges please, or if I were to go out to R, these would all be the same distance. So that point is equidistant out to the points, the 3 points of the triangle. And like you saw in the demo, that point, that circumcenter point, could lie inside the triangle, or it could be right on the triangle, or it could be outside of the triangle. So a few things for you to highlight, and let's read through this together. If you have a triangle, the perpendicular bisectors are concurrent, or in other words, they intersect all together at a point that we call the circumcenter. Now that circumcenter is the point that's equidistant out to the points or the vertices of the triangle. That's important to know. And the circumcenter is the center of a circle that circumscribes, we call that, the triangle. Circumscribes means it goes around the triangle, hitting each of the 3 points. If that circumcenter is in an acute triangle, then it's going to be inside the triangle. If it happens to be a right triangle, then it's going to lie on the hypotenuse. And last, if it's an obtuse triangle, we're going to find the center outside of our triangle. So just something to know. Now, I do not do this very often, and you don't see this in your notes because I want you to write this in your summary. This is actually, I'm just going to tell you what to write in your summary. And in order to do this, I want you to answer this question of what does PPBC have to do with centers of a triangle? Well, I've got a peanut butter cookie here because it helps me remember the letters. PPBC for me might first mean perfect peanut butter cookie. The perfect peanut butter cookie, and we'll talk about that in class because we're going to have a little competition and see who can make the best perfect peanut butter cookie. But it also, and this is where your summary comes in, it also is there to help you remember this. And write this in your summary. To find the center equidistant to the triangle's points, you want to construct perpendicular bisectors, which are concurrent at what is called the circumcenter. So there's a few things I want you to mark here, and also put this in your summary. First of all, let's mark that HD, JD, and KD are all perpendicular bisectors. So let's put in those right angles and those tick marks. So HD hits the triangle at a right angle and chops that side in half. DJ does the same thing, chops this side into equal parts. And finally down here, KD does the same, and it chops this side into equal pieces. So we have these perpendicular bisectors, but highlight this. That means that this point D is the circumcenter. And you should write that down. Point D is the circumcenter of the triangle. And the last thing to remember is that that point D, if I were to go out from point D to point F, or from point D to point G, or from point D to point E, those are all equidistant from point D. And so these three blue lines are all congruent to each other. It's an equidistant relationship. So maybe a set of big 4 tick marks. These guys match. Perfect peanut butter cookie, or to find the center equidistant to points, make perpendicular bisectors, and you're making the circumcenter. Get that in your summary and you're good to go.